Welcome to the final session of the Revman, meta-analysis in Revman. This is actually meta-analysis in Revman 3, but I'm essentially using the same slide deck as the last time. So one of the things that I'll quickly take the opportunity to do is to, revise the work that we have done in the past. Okay, so I will mostly focus on a revision of continuous meta-analysis. Meta-analysis of continuous outcomes, and then we'll take it forward. But first of all, does anybody have any burning questions that you want to ask before we dive in? Anything that's been on your mind since the previous sessions that you want to talk about, then we can move forward.
Excuse me.
Yes, please.
Yeah, I want to ask a question about when you want to pull a study and let's say we have some of the study are cohort study, some are case control, but
Yes.
the exposure and the outcome variable are actually what I'm concerned in mentioning. They are the same.
Okay.
How do we, and then now we are having odd ratio and risk ratio. So how do we pull this study? Do we pull them independently, or we don't pull them at all, or we just pull those that are exclusively risk ratio, that are measuring their effect measure is risk ratio or odd ratio? Then we discard, if you are focusing on risk ratio, we discard the odd ratio. But my concern is that in this scenario, if you have to discard the study because of the measure of the effect measure, we might be introducing bias and we might lose a lot of important study. And also, you promise that you are going to give us a formula, assuming that the effect measure we found in a study is like prevalence, that we can get the risk ratio from the formula or the odd ratio. I wouldn't know.
Okay. Yeah. So can you see my screen? Can you see this paper I just posted on my screen?
Yes.
Okay. All right. So this is the title of the paper. So a lot of, you see, we have been talking about mass media campaigns and diet, right? So in 2013, we did a paper where we looked at mass media campaigns and physical activity. Okay. And, luckily, there is a formula here. So I talked about that formula, and that formula, you can find it in this paper because we did use it to convert. Let me see if I can find it. I haven't looked at it in a while, but yes, this is the formula I'm talking about. Okay. So if you have relative risk and you want to convert to odds ratio, or you have odds ratio and you want to convert to relative risk, you can use this formula. Okay. So it's basically relative risk equals odds ratio all divided by 1 minus the prevalence at baseline in the unexposed, okay, plus the prevalence in the unexposed times odds ratio. So the formula is explained a little bit further here. Okay, what each of the notation represents. Right. So to answer your question, and I pasted the paper in the comment section, so you can pick it up from there. So we don't have to like send this formula around. It's right in this paper. Now, so to answer your question, you have to convert the one measure to the other. So you might choose to convert all the odds ratios to relative risk, or all the relative risks to odds ratio using this formula. Okay. And then you can pull the papers together. All right. So you convert all the odds ratio to relative risk, or all the relative risks to odds ratio, and then you can pull this paper together. And I'm going to show another paper that another old paper of mine that will show you something similar, someplace where we had used it. And I will share the link to this paper as well. Okay. All right. So if you look at this paper, it asks essentially the same question that you were asking. If we have case control studies and cohort studies, what do you do? So this is a paper where we looked at the effect of physical activity on stomach cancer risk. Okay. And, we had a bunch of case control studies. We also had some cohort studies, and we wanted to pull them together in the same meta-analysis. Okay. And that's exactly what we did here. That's exactly what we did here. First of all, we converted all the relative risks to odds ratios, right? So, all the odds ratios to relative risks for the case control studies. And then we pooled the relative risk. So we obtained a pooled relative risk for the entire study. So that's this one. No, sorry. What we did was that we obtained relative risk, separate relative risk for case control studies and separate relative risks for the cohort studies, because we were concerned that, it might not be appropriate to pool both studies. And the reason why we were concerned is because case control studies are plagued with recall bias, right? And we were worried that you might not be truly estimating the same effect, even though it seems to be the same effect. So we pooled them together in the same study, but we don't report the pooled analysis, and we instead report the subtotal analysis. So for our main analysis, we did obtain a pooled estimate, but that's not the one that we are using. What we're using is the estimate for case control studies separately and the estimate for cohort studies separately. Okay. And that's the same thing that we did here. So sufficient physical activity and gastric cancer risk. So we have subtotal for each study type. Okay. So I will paste this paper in the chat as well. And hopefully this answers this question. Cheloka, did I answer your question satisfactorily?
Very well, sir. Very well.
Okay. Okay. Excellent. I posted the wrong paper. So this is one. I posted one paper twice. All right. So any other questions before we go? If no other questions, we can move forward. All right. So welcome again to the third round of our meta-analysis in Revman. So one thing that I hope we might be able to do at the end is do a quick review of what we have learned, but I think we should. Okay, maybe what we can do is that we can start with a quick review, remind ourselves, and then we can dive into talking about heterogeneity, and then we can come back to do a more comprehensive review if we find it necessary. Okay, all right. So remember that we said that meta-analysis is done in 9 steps. So everything that we've been talking about in the live sessions in recent times, the first data synthesis, right? And we can see how extensive data synthesis is. That's the meta-analysis component. You might have noticed that we posted a recent video and set of slides talking about how you would report and write your recommendation. So basically, what we did is, rather than tell you this is how you write the meta-analysis, we instead presented to you fundamental principles of scientific writing. So hopefully that's useful for you in your meta-analysis, but also useful for you in whatever other papers that you're thinking about. If you have questions about them, we're happy to bring Dr. Montayo to come and talk to you, to the class. We can schedule a session, but otherwise, I think that if you watch the video, it should be satisfactory enough. It should be extensive enough to help you answer whatever questions that you have. Okay. Again, the analysis steps. First of all, you create a pooled estimate, and then you explore publication bias, and then the other analysis of interest, the influence analysis, cumulative analysis, assess heterogeneity, and there might be other things too, but these are the most commonly used analysis approaches. Okay. All right. So if we go to our Revman, and the purpose is just to, to just remind you of what the Revman looks like. So this is Revman, and this. So if you open the Revman that I emailed, the last one, this is what the file that we used the last time looked like, right? If you remember, we had looked at dichotomous or multiplicative or ratio outcomes, and we looked at it using pre-calculated data as well as using raw data, okay? And so for pre-calculated data, we told you that you have to estimate the log risk ratio first and the standard error, okay? So you calculate that outside of outside of Revman, and then you just paste it here, okay? And we showed you how to do that. And then once you paste it, Revman automatically generates a forest plot that looks like this forest plot on the right, okay? And you can switch over. So this is random effects model because you can see that here it says random. And you can switch over from random to fixed effects by clicking this sign, okay? Can somebody tell us very quickly, in what situation would you want to use a fixed effect and when would you want to use a random effects model? Anyone, you can just raise your hand, unmute yourself and speak up.
Yeah, thank you very much. I think when the outcome are probably not measured the same way, maybe different instruments measuring the same outcome but in a different way, we want to use a random effect rather than a fixed effect. Thank you, sir.
Yeah, excellent. Yeah, if you have measured the same outcome in different ways and you expect that there is some degree of error arising or variation arising as a result of the fact that you have used different instruments, different tools, different approaches to measure the outcome, you might want to use a fixed effect. But if you think that the exposure outcome relationship are exactly the same, measured similarly, then a fixed effect is just okay. All right. So, and when you look at so here you can click here and the forest plots will pop out and you can look at it in some more detail. So if you look at this forest plot, can somebody just walk us through very quickly how to interpret this forest plot? Somebody else. What are the parameters of interest? What does this forest plot show us? Anyone?
Yeah, let me.
Yeah, 1 second.
Slides back. Okay, the slide.
I will bring it back up. Yes, 1 second. All right. So
this is the forest plot of about 7 studies. It's a fixed effect study, which means the study are generally similar, measured on the same scale.
Yep.
The heterogeneity is 79%, which is considerable. And we had the pool estimate lies between 1.16 to 1.32, okay. and it's 1.23, which means it's significant. It doesn't cross the line of no effect. Okay. So looking at this study, which is basically the effect of media campaign on fruit and vegetable consumption, this favors the intervention, which means for every unit increase in media campaign, we have about 1.24 increase in consumption of fruits and vegetable.
Yep, excellent. Thank you very much. That's a very good way to interpret the study. So we then talked about, and if you remember, we said that this is inverse variance weighting method, right? Then we talked about using the raw data, and in using the raw data, Okay, it's right here. So in the last one we had when we have pre-calculated, we estimated log risk ratio and standard error. But in this case, we just use the direct number of events and the total number in the sample in the media campaigns arm and in the control arm. And we generate a forest plot that looks very similar to the last one. Okay. But in this case, we use the raw numbers. We didn't have to calculate anything. The decision about whether to use raw numbers or to use pre-calculated depends on a number of factors. Okay. If you have all the pre-calculated data, then the pre-calculated data might be better for you to use. If you have pre-calculated data for all the studies, and the reason is that sometimes the analysis that you're looking at is already adjusted for confounding. Okay. In that case, you will not obtain the same value using the pre-calculated data as if you went and used the raw data. If there's adjustment for confounding that has been done, you should always prefer the estimate that is adjusted for confounding. Okay. And the other thing is that sometimes people who have written up the study, they have thought about some challenges of the methods of the study design. And based on that, they have selected a primary analysis as the primary analysis from their study. So if they have a primary analysis and they have other forms of analysis, you should always use the pre-calculated data from that primary analysis. So that's why it's better to use the pre-calculated data rather than to use the raw data. Okay. If you do use the raw data, you will get fairly similar numbers as if you use pre-calculated data from unadjusted analysis. We talked about this the last time. Okay. Now, apart from the forest plot, there is one other kind of plot that we frequently look at in meta-analysis, and what is that called and what is it used for? Can anybody remember?
Funnel plot.
The funnel plot, yes. Okay. And what does the funnel plot tell us?
I think it tells us a bit about is it heterogeneity now? When we look at how they are placed, if they are together or they're out. I can't put it very well.
Okay. So does everybody agree that it tells us about heterogeneity? Or does anybody else have a different idea about what it tells us? What the forest plot tells us? Sorry, what the funnel plot.
Publication bias.
Yes, the funnel plot tells us about publication bias. Okay. Publication bias is the main reason why we'll do the funnel plot. Okay. There are other things that tell us about heterogeneity, and that's the purpose of today's discussion. So this is just a reminder of everything that we've talked about in the past. All right. So the funnel plot tells us about publication bias. And so can somebody who has not spoken today tell us what do we look for when we look at this funnel plot? How would you make sense of it? What are you looking for in the funnel plot to tell you whether there's publication bias or there's no publication bias? Anyone who has not spoken today? We'll just wait if nobody speaks up. No, I think you have already spoken twice, so I think let's have somebody else try. Yes, please, Calvin.
Okay, I just want to say something.
Okay.
From the funnel plot, it's maybe possible to see outliers and those studies that are not within the curve. I don't know if I could call it a curve or the funnel. Yeah.
Within the
and
funnel, okay.
Separate, remove, we could actually remove those studies that may be making a huge difference in the data. Okay.
Okay,
Like the
okay.
outliers. Yeah.
Okay, does anybody else have another set of thoughts that they can share? I think I saw Kevin Londe raise his hand earlier.
Yes, to assess for publication bias in the funnel plot, I think that we have to look for symmetry, that there are equal number of studies on both sides of the vertical line, and that the studies are equally at the same level vertically.
Yeah, okay.
Nearly the same level.
Yeah, okay. So thank you. So thank you, Sharon and Londe. So typically what we are looking at in the funnel plot is symmetry, is symmetry. Is just take a look at the funnel. Don't think too hard about it. Does it look like the studies on the right are fairly similarly placed as the studies on the left? That's the most important thing you should bother your head about, okay? Are the studies on the right fairly similarly placed as the studies on the left? Now, if you have a scenario where there are 7 studies, like in this funnel plot, so you wouldn't expect that there will be like equal number of funnel of studies on both sides, right? There's going to be more than one, there might be more studies on one side versus this other one. So then you look at where are the studies placed. So if you look at this funnel plot, right, it looks kind of like, so these studies that look like they are similarly placed. These ones too, they're not too far away from each other. So I would say that there is really no publication bias in this study. So I think someone mentioned that we might want to look at the studies that are outside the funnel and maybe consider taking them out. I will be very cautious with doing that. Yes, you can, but you have to be very cautious with doing that. You should look at that study and be absolutely sure that this study is really, really different from the others. So it might just be a pointer to some error that you had committed in including the study in the first place, but you have to be absolutely sure, because you don't want to start bending the data to look in a particular way or to look perfect, right? The data might tell you maybe there's an error here, but you have to go back to the paper and absolutely be sure that you have not included the wrong paper. But if you have included the correct paper, then you leave it in as it is. You don't take it out, because publication bias, what does publication bias tell us? Anyone? What is publication bias? Somebody else who has not spoken today. Thank you to everybody who has spoken. This has been very engaging. I like that.
Can I say something?
Yes, please go ahead.
Okay. Publication bias talks about those studies that have not been included, maybe due to language barrier, or there are certain biases the publisher have concerning such studies, although they are supposed to be included in the studies.
Yeah, okay, very good. So publication bias basically tells us that there are some studies out there in the world that should have been published, but were never published, okay? It could be because the editor of the journal saw the paper and the sample size was small and the results did not fit the pattern that the editor expected to see, and so they rejected the paper. So really, publication bias, it's a bias because the paper is not published because of its results, because somebody saw its results, looked at it, it didn't fit what they expected to see, and so they chose not to move it forward. Okay, That's publication bias, because somebody has biased the literature that we should be seeing. And because somebody else has done that bias, now you're stuck with 7 papers that, maybe instead of 8. That's really what publication bias is. So that's important to bear in mind, as we go along. And that's one of the most important concepts in meta-analysis. All right. There is one final set of concepts that I want to ask about in this forest plot before we move forward. And I think that somebody had hinted at it earlier, and that is heterogeneity. Okay. And that's what we're going to talk about today. So, but I want to, first of all, test the waters and see if there's anyone who already kind of understands what heterogeneity is. So here we have heterogeneity chi-square to be 28.44, and we have a p-value less than 0.0001. And then we have the I-squared to be 79%. Okay, so can you tell us, what do these numbers mean? Somebody else who has not spoken today, who wants to give it a shot before we allow others who have spoken today to go again? Anyone? It's okay to not have it correct. We're all here learning together. So
let me try. I
okay.
think when the p-value at a scale of 95% confident interval, when the p is greater than 0.05, we say that there is no publication bias.
No. So that is so we're talking about heterogeneity right now.
Yeah. Okay.
Yeah, we're talking about heterogeneity. So publication bias, we talked about it for the funnel plot. Okay. There is something called the Eggers test. And I think that's the one that you're talking about. We don't have Eggers test here. We don't typically get Eggers test from the forest plot. So here we're talking about heterogeneity. So if you look at the p-value less than 0.0001, Chiloka, can you tell us, do you think that this is statistically significant and so there is heterogeneity? And if so, what do you think about this 79%?
Yes, the p-value is less than 0.05.
Yeah.
So it's significant.
Yeah.
It's significant. And the I-square, which is the heterogeneity measure, is considerate.
Okay. So yeah, so basically that says that there is a lot of heterogeneity. What is the maximum value of the I-squared?
Between 80 to 100.
Yeah, so 100 is the maximum value. Very good.
Yes.
Okay, thank you very much. So I guess that's helpful. So I will just skip along and introduce heterogeneity. I think we've just had a very quick introduction to it. So let me exit here so that we don't have to go and start all over again. And then I will. Okay. All right. So let me explain what the concept of heterogeneity is. So the reason I wanted us to come back to Revman first to teach it before we then go and teach in R is because, this would allow us to talk about the concept in a little more detail, and we'll show you what if you can do it in Revman. Okay. So heterogeneity is really the idea that when you look at the pooled estimate from a meta-analysis, right, there are some studies that contributed to that pooled estimate, right? So maybe 7 studies that you have pulled together. And those studies, they differ in certain respects. It might be that one study includes the elderly more than it includes the young. It might be that one study has more males than more females. It might be that one study has more obese people than the other. And that these are the characteristics that are really driving the results that we're seeing. So you might say that media campaigns, right? That if you do a media campaign, you will be able to impact the intake of fruits and vegetables, right? But someone might tell you that, well, maybe if your study was conducted among young people, you would find that result. But if you did your study among the elderly, you might not find an effect that is so large. You know, maybe media campaigns do not work so well among the elderly. So maybe you need to design a different kind of study. Maybe there's something else that you have to do that would work in the elderly. That's really what the concept of heterogeneity is. So if you think about effect modification in epidemiology, right? Heterogeneity is sort of like effect modification, if you understand what effect modification is. So the results that you're seeing in each individual study, they differ based on certain characteristics that the population has, or that the study design of that study has, or that maybe because of the way the outcome was assessed in that study. And maybe that's what's driving the results you think you're hypothesizing, and not that, so, maybe that's what's driving the results. And that's why it's different in some way from the other studies that you're looking at. So in heterogeneity, you're trying to investigate. So if you have this pooled estimate of maybe media campaigns and an intake of fruits and vegetables, you don't just fold your hand and say, yes, media campaigns always work if you have always work to increase the intake of fruits and vegetables, right? It might be that maybe it doesn't work so well in some people. Maybe it doesn't work so well in the elderly. Maybe it works very well in the obese, but it doesn't work so well in the undernourished. So teasing it apart, the data, understanding the data in more detail, that's what heterogeneity tries to do, okay? It might be population characteristics. It might be, intervention details. Maybe in one study, you're looking at oral versus IV iron, and the effect that you're seeing is present in the people who have intake based on the oral route, but not those who have intravenous, right? It might be the duration of exposure. Maybe you have asked some people to exercise for 2 weeks, but you've asked some other people to exercise for 6 months, and then you're comparing the BMI in those two groups, and then the effect that you're seeing is due to the duration. Those who exercise for longer, right, they had lower BMI. Or it might be something like an environmental exposure. Maybe in an environment, you're noticing that there's an increased risk of cancers. And someone said it might be the particulate matter in the air. And so the duration of exposure might be people who have lived in that area for 10 years compared to people who just moved there last year. So maybe people who have lived there for 10 years, they have been exposed to the high particulate matter concentration in that area for such a long time. Okay, the duration of exposure is longer in this group of people. And that's why you're seeing the effect that you're seeing. Okay, teasing this apart is a very important part of meta-analysis. Helps to add color to your analysis, helps you to understand what you're seeing. Okay, and this is a concept of statistical heterogeneity. It's the idea that the differences in the magnitude, that there are differences in the magnitude and the direction of the point estimates that you're looking at in the individual studies, and they together are driving the pooled analysis results that you have. Does anybody have questions about this before we go on? Any questions? All right, so I'm going to assume that that's clear. So the way that we then assess heterogeneity is that, I don't know if you're familiar with the concept of hypothesis testing, right? So this is the null hypothesis, and this is the alternative hypothesis. So the null hypothesis is basically saying that all of the studies are the same, right? But the alternative hypothesis is saying at least one, the finding from one study is different in some way, and so what we're trying to tease apart is that difference. And there are two ways that we frequently look at heterogeneity. First is the Q statistic, and the second is the I squared. And in reality, they are both the same, okay? the Q statistic and the I squared, they're kind of telling us the same, just different parts of the same thing. Because the I squared is calculated from the Q statistic. Now, when we look at the Q statistic, very often what we care about is the p-value. Okay, that's what we most often care about. We look at the Q statistic. This is how it's calculated. It's based, there's also the weights that are involved here, the estimates. But what we really are looking at most often is the p-value. And if you remember when we looked at that p-value from Revman, this p-value less than 0.0001, right? The way we usually look at p-values is to compare it to 0.05. It's less than 0.05, we say it's statistically significant. But in this case, what we're really interested in, what we often do is look at it against 0.10. And the reason is because the Q statistic is not very well powered. It's not a really strong test, okay? So the p-value will often go outside of 0.05. Well, it's very often that we'll find p-values that are above 0.05 just by chance alone. So that's why we then are looking at, we use a threshold of 0.10 instead for the Q statistic, okay? But we then use the Q statistic to calculate the I squared so that we can obtain a percentage, right? And you remember Chiloka was telling us that 100% is the maximum. And if you have between 80 and 100%, then you say that this heterogeneity is considerable. If you have between 60 and 80, we say it's substantial. If we have between 40 and 60, we'd say it's moderate, okay? So if you're doing your meta-analysis, you would report the p-value for the Q statistic and the I squared, right? And you will say, oh, this I squared is whatever it is, you say maybe is 78, and so that's substantial heterogeneity, okay? That's it. That's really the concept of effect heterogeneity. But the question then is that, what do you do next? What do I do with this information, right? So these numbers you will obtain from the forest plot, like we saw earlier. If you do it in Revman, it will automatically generate the numbers for you, and that's just here. So this is the Q statistic here is 28.44. It's a chi-squared value, and it has its own degrees of freedom. But this is the p-value of interest for the Q statistic, and this is the I squared. So the I squared here is 79%, which is substantial heterogeneity. Okay? If you have any questions at any point in time, please stop me and we can go over concepts. So the question then is, so what do I do if there is heterogeneity? So what do I do next? You've seen that the p-value of the Q statistic is less than 0.1. What should you do next? If your I squared is above 40, okay, people will want to see that you explore heterogeneity in some detail, okay? Sometimes you should decide from the beginning that you want to explore heterogeneity regardless of what the I squared is, okay? And that's good practice. So you're not deciding based on what you see. So you can either do that, or you can decide, oh, if the p-value, if the I squared is greater than 40, then I will explore heterogeneity in some more detail. Now, if the I squared is greater than 80%, when you have considerable heterogeneity, there is a higher level of assessment that you're expected to do. You want to, first of all, go back at your data, look at your data again and make sure that you haven't made errors. Look at the relative risk and confidence intervals that you have input. Sometimes there are errors from typing. Check and make sure that that everything is correct. Look at the data that you extracted, make sure that you extracted the correct thing. And then you input the correct thing in the software. If heterogeneity is greater than 80%, there is a school of thought that you should completely discard your meta-analysis and just say, this meta-analysis could not be done because the papers the heterogeneity was considerable. That's one way, and that's completely up to you to decide depending on what you think. And you might decide based on your understanding of the literature. It might be that because you know the literature, you can see that maybe what's really driving this heterogeneity is that the instruments that were used were considerably different. They were so different that maybe you can't reasonably, or a reasonable person can argue that this is not the same type of instrument. Like maybe depression, for instance, someone might say CESD and GHQ 12 or whatever are not assessing the same underlying concept. And so you should not pull them together. So if that's what's driving your heterogeneity, if you suspect that that's what's driving your heterogeneity, you might say, okay, we're not going to do a meta-analysis here. We'll just report the results for each study. And that's acceptable. Okay. If you do decide to do a meta-analysis, then you want to explore heterogeneity in some detail, and there's some approaches that we usually take, and we'll talk about some of them. The first one is a meta-regression. The second one is to obtain prediction intervals, and the third one is to do a subgroup analysis. Okay. In subgroup analysis, basically, so those are the three steps. So there's prediction intervals, meta-regression, and subgroup analysis. But you should go back, like I said, and check your work again and make sure that you have included the correct studies. Also, it might be the case that some studies that you have are meaningfully different from the others that you have included, and you might take a decision as to whether to take them out and repeat your analysis. Okay. All of these decisions you have to document in your paper and say that this is what you did. This is how you came up with your final estimates. Okay. Any questions? Any questions at all?
Yes, sir. Yes.
Yes.
Yes. So now, when I statistic is above 80, and then we remove the meta-analysis from our study, will it affect the acceptability of such research or its quality?
It won't affect the acceptability. It's actually, if you write it up and say, you have to say that you did this meta-analysis and you obtain an I-squared statistic of more than 80%, but you're not reporting the meta-analysis because I-squared was considerable, the heterogeneity was considerable, and you do not believe that doing a meta-analysis here is the correct approach. So you will explain yourself like that, and it will be acceptable. Sometimes what you might do is that you will include that meta-analysis finding in this supplement of your paper and say, so that if somebody who is interested in the meta-analysis, you would say that it's in the supplement, but in your main analysis, in your main paper, you don't think that this meta-analysis is acceptable because the heterogeneity was very large. You would explain that. If you explain it, it will be acceptable. Okay. So,
Thank you.
yeah, you're welcome. So that's the thing. As long as you explain what you're doing, then it will be acceptable. So we'll take a moment to then go through each of these concepts: the prediction interval, meta-regression, and subgroup analysis. And then we'll see which one we can do in Revman. Okay. So this is just showing you the I-squared 79% that we had looked at earlier, so I'll skip along. All right, so meta-regression. So I think that this might be a good place to stop and take a 5-minute break, and then we can when we come back in 5 minutes, we can delve into each of the, yes, before the break, we're talking about the concept of heterogeneity, and we said that It's essentially the idea that the individual studies that you have are different in many ways, right? And you want to be able to understand the ways in which the studies are different. And we said that there's a Q statistic which gives us a p-value, and we read off that p-value at 0.10. Okay, and that the reason why we do that is because the test is underpowered. And then we can use the Q statistic to calculate the I squared, and that I squared, the maximum is 100. You will get a value that's a percentage. It might be 79%, 80%, 40%, and there is a classification scheme that will tell us whether this is moderate heterogeneity, limited heterogeneity, substantial, or considerable. Okay, so that's what we're talking about before we took a break. Now, there are a number of steps that we will then take if there's heterogeneity. First, typically that we will do is metaregression. Okay, metaregression is really just us in trying to understand whether the individual studies differ. We look at the characteristic and then we model that against the values that we obtain from the estimates in each study, right? So you're essentially repeating that the meta-analysis and including a variable, and that variable is the variable for the characteristic they're interested in. So say age, for instance, you might say that you might classify the studies and look at what proportion of people in that study were less than 40, 40 to 65, and greater than 65. So you create a variable for that from your study, and then for each study, and then you include that in the regression, and you obtain a p-value. Okay, that p-value is the p-value of meta-regression. And essentially, you just look at this p-value. If it is less than 0.05, you say that it is significant. If it is greater than 0.05, you say that it is not significant. So like this, for instance, 0.049 for female and male, you say that this is significant. For this one, 0.56, you say that it's not significant. That's meta-regression. We use the p-value to make an inference. Let me explain this again. Basically, in meta-regression, we look at each individual study that we have, and we create a variable that tells us where that study stands. So say female, for instance, what's the proportion of females in that study? It might be 59%, 69%. And then we add that variable into the regression model. Okay. And it's typically a linear regression, for a model that includes the effect estimates for each of the individual studies. So when we model that, we obtain a p-value that tells us to what extent those studies differ based on the proportion of females that they have in the study, or the proportion of Africans, of studies from Africa, or that kind of thing. So you create a variable like that, and then you include it in the regression model, and then you obtain a p-value. Let me show you the kind of variable that I'm talking about. So 1 second. So if you remember that metadata data set, and I'm just going to show that in a moment. If you remember this metadata data set, we had the relative risk, the lower relative risk, and the upper relative risk, and then we had the log effect size. You remember this data set, right? But in addition, we have these kinds of variables, right? Which is country, and for each country, so maybe 1 is Australia, 2 is Canada, 5 is the US. This variable we can include in the model and then obtain a p-value. Or we can include this variable that tells us whether the study is from Africa or not. or this variable that tells us what the coverage of media campaign is for that for each study. So this one had a 65% coverage. This one had a 23%. This was 95%. You include this variable in the model, and then you obtain a p-value. That is meta-regression. It's very straightforward. It just has a big name. Okay. Or this one where you've already created the variable, and you basically dichotomous variable here, where we have said, is this above 65 or is this above 50 or lower than 50? Yes, please.
Yes, sorry, thank you, but I'm a bit confused with the model. Maybe you're explaining it later. What is the model?
Okay.
Regression
so,
model, I mean.
Yeah, so how do I explain this? So if you remember that in Revman, these pooled estimates that we obtain in Revman, they are obtained based on some mathematical model, right? So that's basically what the model is. There is some underlying mathematical formula that you have used to obtain this. In this case, there is a linear regression model that is used. That basically you do a linear regression of the effect sizes and the confidence, the effect sizes from that study, and you compare them. But the covariate of interest, the predictor of interest for that model is, say, maybe what proportion of people in that study were female or male. Okay. And then it tells you whether there's a statistical significance, and then you obtain a p-value. That p-value is the entire process of doing this modeling is what's called meta-regression. It's a regression of the meta-analysis. It's kind of like big words, but the idea is that you obtain a p-value, and that p-value, this one, tells you whether there's a statistically significant difference in the studies by what proportion of people in the study were less than 40 or 40 to 65, or based on what proportion of people in the study were female or male. Okay. That is meta-regression. Is this clear? Is this clear to everybody? If you understand it, can you do a thumbs up? If you don't understand it, can you do a thumbs down? And then we can try to go over it again.
Sorry, thank you very much for the lecture. Please, is there a format for us to calculate the linear regression? Sorry, I'm not following you up, but I've started to be serious right now. But I just want to ask,
so you won't do it yourself.
Yes. Is there a format for?
Okay, yeah, you will not do it yourself, right? I'm just explaining it to you that this is what is happening under the hood. So yeah, you're not like going to bring out a pen and start calculating anything. No. But it's for you to understand that this is the concept and this is the data that you need. So the data that you need is this kind of data that just tells you for a variable called Africa is a study from Africa or not from Africa. So Nigeria is from Africa, so the variable is 1. If Australia is not from Africa, the variable is 0. So you create a variable that looks
You are muted. Can't hear you.
The volume is off.
Okay, all right. Can you hear me now?
Yes, we can hear you now.
Sorry, I lost my audio for a moment. Right, so you will create the variables and then you use it in the analysis. Okay. Now, the reason why I've gone through all of this explanation is just to tell you that this is what's happening under the hood. You're not going to calculate it by hand. You will use software. And if you attended the SPSS session, we already showed how to do this in SPSS. In Revman, however, we are not able to do meta-regression in Revman, unfortunately, right? We're not able to do a meta-regression in Revman, unfortunately. And so, we have to then do a different approach in Revman, and that's the subgroup analysis, and I'll show that. But before we go to the subgroup analysis, I want to talk to you about the concept of the prediction interval. And I see someone has a comment in the chat saying that because the sample size for this regression is small, the results may not be stable. That's correct. That's very correct, right? So it is it's an imperfect approach. I'm not sure that a bootstrapping is done in this analysis, and that's why it's often better for you to do a meta-regression based on when you have large number of studies. Some people say that you should only consider a meta-regression when when the number of studies is more than 10. Okay, but that's when you begin to have enough power for this analysis. I will say that you're better off presenting the estimate still. You will have wide confidence intervals, right? But if you do find a statistically significant finding, if you do have a finding that is significant, then you will know that there's really something happening there. It's kind of like the way that you think about it. If it's significant, there's something happening there. If it's not significant, it doesn't mean that it's not important. It's not important for you to bear in mind. So this is just sort of like a suggestion. It's not a perfect methodology, is basically what I'm saying. Okay. All right. So once you then obtain the p-value, the next thing you will do is to predict the estimate. So you will then, not that you will calculate it yourself, but as part of that regression that you have done, the software can tell you if you had a study where everybody was male, okay? If you had a study where everybody was male, like this is what you would have obtained. So let's go back here. And this is a meta-analysis looking at the effect of some micronutrient on acute respiratory tract infections. This was from a study that we did during the time that COVID was raging. So this is the pooled estimate is 0.96, all right? And this is the confidence interval. But in this study, you had males and females, and you know what proportion of people in each of the studies was male. So based on that, you do a meta-regression and you obtain 0.049. You could then predict a scenario where everybody in the study was male. So if you had an all-male study, what would your pooled estimate and confidence interval have been? Or if you had an all-female study, what would your pooled estimate and confidence interval have been? So in this case, because you can see that the the confidence intervals here do not cross null, you can make the conclusion that this intervention is significant in males, but not in females. This intervention is significant in males, but not so in female, right? That's the impression that you will then make here. In this case where the meta-regression is not significant, right? You might then look at for each continent, or you might not. You might say, oh, if it's not significant, we won't go forward. Or you might decide that we would look at it whether it's significant or not. Okay? This is the concept of a prediction interval, is that you assume that what if a scenario where everybody in each of the studies were male, what would you have obtained? So this helps you to understand essentially what's going on under the 0.96, under the hood here. And this is the concept of meta-regression and prediction intervals. Unfortunately, we cannot do that in Revman. And so in Revman, what we do is we subgroup analysis. Okay? But before I keep moving on, I want to ask if there are any questions. Or is this perfectly clear? I'm worried about the silence.
It's clear.
Okay. Anyone else?
On my part, I'm trying to understand, sir.
Okay, so what do you think? Which part do you think is challenging for you, Luther?
Okay, from the table, I'm trying to understand how, first of all, the essence of meta-regression itself. So that
yeah, okay. So meta-regression gives us one p-value, right? That just tells us, is there something happening here? Is age an important factor driving the estimates that we're seeing? So we have 10 studies, 15 studies that we are pulling together. And each of those studies have come from different populations, some in the elderly, some in the young. And we're seeing that maybe those in the elderly are significant and those in the young are not significant. So you might be doing a study where you're looking at the effect of income, right, on how many days a person spends in the hospital, right? And so you have some people who are in their 20s, and people in their 20s are not likely to have as large an income as people who are in their 50s, for instance. And when you do this study, the study is finding that income is related to the duration of time a person spends in the hospital on admission or something like that. But somebody tells you that, it might be age actually that's driving these results. Or maybe if you look at this study by age, you might see a different set of, the pattern of the results might be different. Meta-regression is how we disentangle that and how we figure out, is age an important factor driving the relationships that we're seeing? Or is sex an important factor driving the relationships that we're seeing or not? That's what meta-regression does. So we get one p-value, okay, that we read off. And if that p-value is greater than or less than 0.05, if you're using the threshold, then you'll say, oh, this is statistically significant. You could do meta-regression, or you could just do a prediction interval. So it's not mandatory that you have to do both. Okay, so you could do meta-regression, or you might do a prediction interval and predict what you would have found if everybody in the study was above 65, or everybody in the study was between 40 and less than 65, or everybody in the study was less than 40, or everybody in the study was male. So you predict what estimates would you have found. You would tell the software to tell you, to predict for you, what estimates would you have found. And based on that, you will say, if all these 10 studies were conducted among males, this is what we would have found. But because we have some males and females, this is what we are finding. That's really what meta-regression and the prediction intervals do for you. The difference between prediction interval and subgroup analysis, it's an important distinction, okay? The difference is that in the prediction interval, you're using statistical approaches to guess, what will you have obtained if you had male only studies. It doesn't mean that you do have male only studies. You might not have any male only studies, but you have some number that gives you an idea, or maybe some studies had 50% female, some studies had 20% female, and you can use that to guess. In a subgroup analysis, you do no guessing. You look at the studies that were conducted in Africa, and you pull those together, and you do a small meta-analysis for studies from Africa. You look at the studies from Asia, you pull those together, and you do studies from Asia. You do not guess at all. You just, it's what you have, and that's what you use. The problem of subgroup analysis is that, so say here in female, for instance, we have 55%. In prediction interval, we can use that to guess what we would have obtained if we had 100%. But for subgroup analysis, we don't have any, if we don't have any study where females were 100%, we cannot obtain a subgroup analysis based on sex. Let me explain that again. In the prediction interval, we are going to guess based on all the data that we have obtained. We have all this relative risk and standard errors, and then we're going to do a regression. And then we also have the proportion of people who are female, proportion of people who are male in each individual study. And, we include that in the model. Now, we can use that to guess what we would have obtained if everybody in the study was female, or if everybody in the study was male, right? That is prediction interval. But in subgroup analysis, you have to have the exact data. That means that you have to have studies where everybody is female, and then you can pull that, or studies where everybody is male, and you can pull that. So what you often have with subgroup analysis is that you can do a subgroup analysis where you have studies from Africa or studies from Asia, and we'll look at that. That we can do in Revman, okay? So in Revman, for instance, so if we go back to Revman, and this is our, so if you go back to Revman, let's see, we will create a new subgroup. Right, so if you go back to Revman, so you click data and analysis, and you have the name comparison 5+. You want to introduce a subgroup. So introduce a subgroup, you will, so say you want to introduce a subgroup for, let's use this one, 5+ fruits and vegetables. So if you right click, so if you click on the outcome and you right click, you will see here it says introduce subgroup. So if you click introduce subgroup, sorry, it's this one. Right, so if you click introduce subgroup, then you can then edit the subgroup. So here you can edit subgroup. Wait, hold on, sorry. So this subgroup, so if you have this subgroup, you can select the studies that go in each subgroup. All right. So right now you have all the studies in the subgroup, which is not what you want. So the question that you have is what studies fit that particular subgroup. So for instance, if the data that we're interested in is coverage, right? So if you go back to this metadata Excel, someone asked, does this mean that the data set has to be homogeneous in subgroup analysis? Yes, that's what it means. So if you have this metadata Excel, you can see that we have for coverage greater than 50, you have some studies where people, you have some studies where the coverage is greater than 50%, like this one, the coverage is not greater than 50%, 56 greater than 50%. So you can see that the first study, Abioye 2021, this fits, right? But the next one doesn't meet, is not in the subgroup, so you take that out. Then the one that goes after it, that's the Adijare, that's in the subgroup. The next one is not in the subgroup. And so as you can see that as I'm clicking this, clicking this checklist, the study itself is leaving the, what's it called? The forest plot, right? And now we have, and then there's Banning Bay as well, that's in that meets the criteria, Abioye that does, and then this one does not. So we end up with 4 studies that meet this criteria. So that is people who are the studies where the individual, where the coverage was greater than 50%. I'm still trying to, yes, rename. Okay. Coverage above 50%. Right? And so the next thing that you want to do is add another subgroup where coverage less than or equal to 50%. Okay? And so you can edit the subgroup. You can edit subgroup. So this is that subgroup. Ideally, you should be able to move this here. Forget how to do that. But you can add the data from here and add studies. Okay, I haven't taught this one very well. So Adebi, Anipeze, and Igor Sage are the ones that are in this subgroup. Wait, no.
You need to hold down the shift key before you can.
Yes, I wasn't paying attention to that. Sorry. Thank you. And so you can essentially just copy these numbers. That's for Adebi, and you paste it here. And this one, Abioye, that's this one. And then Igor Sage. So now if you look at the forest plot on the right, you can see that there are 3 diamonds. Okay. There is this diamond that's for everything. And let me pop this up so we can see. So there are these 3 diamonds, this one, and that one. And we can still clean this out, remove this specific studies, and maybe I should do that first. You can tell that I haven't reviewed this class before I came on. All right, so let's just keep going. So basically what you want to do here is that, so you have this forest plot, right? But this forest plot has two subgroups. One where the studies are above 50% for studies, and one where the studies are less than or equal to 50%. And we can edit out these numbers, and I'll figure that out and I'll tell you how to do that later. I think that the way that I added the studies into the subgroup was wrong. But basically what you will get a forest plot that looks like this. And you have to make up your mind if you think that these two pooled estimates are significantly different from each other. So what do you guys think? Do you think that this is meaningfully, not necessarily significant, but meaningfully different from this? So this is 1.53 and this is 1.17.
Yes, I think so.
Yeah, I think so too. But yeah, that's completely up to you to decide. You might look at the fact that, you might look at whether the confidence intervals overlap, right? So like this is the lower confidence interval here is 1.38. The upper confidence interval here is 1.27. And so you might say that these estimates are statistically different from each other, but that's another approach to look at it. Or you could eyeball it and say that these look like they're meaningfully different, which is a more subjective approach to it. So let's do this again so that I can show you how to correctly add the subgroup. So what I'll do is that I'll delete and just quickly go over it again. All right. Okay. So all right. So let's try it for another. Maybe we can try it for the pre-calculated estimates. Okay. All right. So here, what you will first of all do is that you right click and you introduce a subgroup. Okay. Then you will edit the subgroup. I hope I don't make the same mistake again. So you will rename the subgroup rather, and call it maybe coverage greater than 50%. And then you will create the second subgroup. Okay. And so we have the pre-calculated. So you have two subgroups. Now you need to edit the subgroup to add the data to it. Right. Okay. So here. So you can see, so rather than do it here the way I did it earlier, what you have to do is that you do it here on the left, in this headline, where you have these headlines here. So this study, you can just simply click each study and move it to the relevant subgroup. So the first one at less than or equal to 50, let me look at my metadata again. So this is greater than or equal to 50. Undo. Okay, so this Abioye, you click it and you move it down. And now you see that Abioye is here. And then the next one is Anikpezie. You click and then you move it down to the subgroup where you want it to be, right? And then the next one is the ego or sage. You click it and you move it down to the subgroup where you need it to be. Now, when you look at the forest plots, it looks exactly how it should be. So I hope this is clear. Or should I do this again? So the first time I had tried to edit the forest plots just by editing the data, and that was the wrong way to do it. And that's why we had all the studies come out in the forest plots with gaps. But this time around, we have the forest plot coming out exactly how it should, right? And here we have 3 diamonds, okay? And this is the overall pooled estimate. This is the subgroup for coverage less than or equal to 50. And this is the subgroup for coverage above 50%. Okay, and you can compare them by just looking at whether it's meaningfully different, or you can compare the confidence intervals to see whether they overlap or not. Any questions? Oh, this is perfectly clear. We can keep going. All right, so I'm going to assume that it's perfectly clear. This is the forest plot that we obtained, right? This is what it looks like. And this is the funnel plot, right? So if you look in Revman and you click the funnel plot, that's the forest plot. This is the funnel plot. So you can see that Revman gives you a funnel plot that is color coded. Red are those in one subgroup, and green and black are those in the other subgroup. And you can see from here that there's actually a pattern that arises in the funnel plot as a result of the coverage. So coverage is a key determinant of the findings, right? That's why in all the cases, we can see that the studies are on either side of the midline. You know, it doesn't always look like this, but that's because these studies are meaningfully different from each other. Okay. All right, so that's subgroup analysis. Do we have any questions?
Yeah, I have a question, sir.
Yeah, please ask it.
To be sure, from what I've seen now, it seems the meta regression, I don't know if I put it, meta regression analysis, and the other one that is the predicting, they seem to go together.
Very often, yes, they go together, correct.
Together, okay.
Yeah.
Okay, and it's almost like one is looking for, permit me to use the word confounders, when we do for normal studies, where you are looking, okay, what factor is associated with this? Then looking at the, well, I won't, just to help me understand it better, but I think it's
so they're not really confounders, but I get what you're trying to say. So they're more like effect modifiers.
Okay.
Yeah,
okay.
So they're more like effect modifiers, where one factor is related to, you know, one factor affects the relationship that you're seeing. It might be in one direction when the effect modifier is A, versus if the effect modifier was B, if you're doing A versus B, or 1 versus 0, something like that.
But I think the final thing then is, it is still the researcher that would determine the variables to consider to check.
Yes.
Thank you.
It is the researcher. And the researcher will make that decision based on the researcher's understanding of the subject matter. Okay, so that is why, you know, you still need subject matter expertise. You will not be handing over your knowledge to the software. You have to guide it. Yeah, okay. All right. So changing gears, the next set of analysis as well, Revman is not really good at doing them, but what we'll do is that I will use this opportunity to introduce you to most of these concepts. And then next week, I'll show you how to do it in R if you're interested in learning how to do it in R. The important thing to note is that Revman is a highly valuable tool, but it's not perfect. As I've shown you today, there are aspects of the methods that Revman is not able to do, and there's things that Revman then does. So to examine heterogeneity, you can do subgroup analysis, which is not the perfect method, and I showed you that. Next, we'll talk about sensitivity analysis, right? In sensitivity analysis, what you really are doing is that you're taking a step back, you look at the question that you've asked, and think about the decisions that you made, right, at every point in time, and ask yourself, what if I had made a different set of decisions? Okay, what if I had made a different set of decisions? And then think that if you made a different set of decisions, what results would you have gotten? And this can be throughout the time, from beginning of when you're doing data extraction, when you're selecting papers. What if you had only what if you had included abstracts that never become full text papers? What would you have found? What if you had only included the elderly, or maybe you had defined being elderly based on 65 in your study, and someone says, oh, maybe that is too stringent. Can you use studies that define based on 60, right? So those kinds of decisions that you make, you go back, you make a different set of decisions and repeat the analysis and look at how your results then differ. It's basically, you go back and repeat the meta-analysis all over again. But just so you already have extracted all that data, and then you just, maybe you only included 9 studies in your main analysis. In sensitivity analysis, there's one more that you took out. You repeat the analysis and include that one. That's basically what sensitivity analysis is. Or maybe in your main analysis, you have 9 studies and you think that 3 of them are different in some way. Maybe 6 of them are cohort studies and 3 of them are case control. So now you include the case control studies, or now you take out the case control studies and repeat your analysis. That's basically what sensitivity analysis is. I won't spend so much more time on it, but do you have any questions? The question of how do you operationalize this in Revman is basically that you go back to Excel sheets and maybe take out some studies that you didn't want to include, or that you included before and now you don't want to include, or that you didn't include before and now you include them, and you pitch your analysis and you present the forms of analysis and say, if we had done this, this is what we would have found. That's basically what sensitivity analysis is. Okay. The next one is influence analysis, and I don't think you can do this in Revman either. I have looked, and I didn't find it. Now, for influence analysis, what you're really doing is that you have a meta-analysis that has maybe 15 studies, right? You go back and start taking out each study one by one. You take out the first one, you repeat your analysis, look at how your results are different. You add it back. You take out the second one, you repeat your analysis. What result do you find? You add it back. You take out the third one, you repeat your analysis. This is basically the concept of a leave one out analysis. You repeat the meta-analysis many times. Each time you're taking out one and you're adding it back. You're taking out one and you're adding it back. That is influence analysis. If you find that when you removed one study, your result became so different, then you will conclude that that study has a large influence on your findings. Okay, so let me show you what this then looks like in the so typically, if you do an influence analysis, this is an R output for influence analysis. and you have a p-value, or sorry, you have a pooled estimate of 0.38, right? Now, what you're doing is that each time you take out, maybe you take out this one, this is what you have, you take out this one, this is, no, sorry, I'm explaining this one. This is the main analysis, right? This is the main analysis on the left. This is what the forest plot would look like. On the right-hand side, you have the estimate when you take out study one. So if you take out study one, in the main analysis, you have 0.38, but when you take out Abioye 2021, you obtain 0.37 as your estimate, and your p-value is less than 0.001. And then you repeat the analysis, you add that back, you repeat the analysis, you take out ADD, and this is your new pooled estimate, right? You take out Adejare, you add the others back, you take out Adejare, this is what you then get. So each time you're looking at the estimate that you're finding and asking yourself whether these numbers are significant, are meaningfully different from 0.38. Okay. And then you're looking at the p-values. So maybe now you have less than 0.01, but maybe when you do one of them, you now get 0.12. So you know that that particular study that you took out has a major influence on your analysis. Is this clear? Or does anybody have questions? I'm going to stop here and just wait and hear what thoughts you guys have.
Francis?
Yes.
Sorry. Does it mean that since we can then do this on using Revman, then is it possible?
You can do this using Revman, yes, but that means that you will do it manually.
Manually, okay.
Yeah.
Okay.
Unlike in R, where you will just run the code and then it will generate it for you. Okay. So if you do it in Revman, you have to create this table yourself and you can compare and make up your mind what you think. Unlike if you use R, it might even generate a figure for you that will show you, as the numbers are moving here and there, here and there. I know I used to see that in Stata, but I didn't figure it out in R, so that's why I don't have it here. Okay. Any other questions? All right, so the next one is cumulative meta-analysis. We have a question. Someone asks if it can be done in SPSS. I believe so. I believe so. And let me see. Let me see if I can fold the SPSS slides that we did. So here. No, it cannot be done in SPSS, not unless you do it one by one, like we're just talking about in Revman. So at the end, we have this table. I'll get to it in a moment, that shows you which aspects of everything that we have taught you can you do in Revman, in SPSS, and R. Okay. And if it's a tick, then you can do it. If it's an X, then you can't do it. But you might be able to find a way around it if you understand it. So like the influence analysis, you can do it yourself, but that means you do it manually. Okay. The next final one I want to explain to you is cumulative meta-analysis. Now, there's some research questions where the results that you obtain differ based on when the study was done. For some reason, for whatever reason. Okay. And I can give you an example. If you do a lot of research in HIV, right, especially when it's related to like HIV outcomes, clinical outcomes, you will know that the ways that patients who have been treated for HIV, and if you're a clinician, you will know this too, has changed over the last 25 years or so. Initially, HIV patients were not getting any antiretroviral therapy because antiretroviral therapy did not exist in a way that was meaningful, effective, or it was not available in many countries. And then it started to become available, but it was only just zidovudine, and maybe it was just zidovudine around the time the woman was going to have a baby. There was no real effective antiretroviral therapy to provide to patients during care. And then, there were studies that were done, and then zidovudine became more widely used. And then you start having combination antiretroviral therapy. And then you started to have highly active antiretroviral therapy. And then that highly active antiretroviral therapy was initiated based on the severity of the person's HIV condition. So initially then, the thinking was that if a person had stage 3 HIV disease, or the CD4 count was less than 200, then you will say, oh, let's initiate antiretroviral therapy. But those cutoffs started becoming more liberal. And then at some point, 200 became 350. If a person had 350, then you initiated antiretroviral therapy. But today, if a person is diagnosed with HIV today, then they're initiated on highly active antiretroviral therapy, because we know that highly active antiretroviral therapy helps to prevent the spread of the disease. Okay? Why do I go into this story? Is to tell you that over the years, the story of HIV treatment has differed. And so there are some studies that would have been conducted, depending on the time in the HIV epoch, depending on the time when they were conducted, the results that you have might be different. And a good example is nutrition, right? There were those years when an HIV patient did not get any antiretroviral therapy, and the only thing that you could do for them was teach them about good nutrition or provide nutritional supplements to them, right? And even if you did provide nutritional supplements to them, you saw some effect. It wasn't radical, and then the effect of the nutritional supplementation on HIV began to differ depending on whether they were getting antiretroviral therapy, what antiretroviral therapy they were getting, how sick they were when you initiated it. Now, in cumulative meta-analysis, what we're trying to see is whether the pooled estimate that we're obtaining, whether it differs by time. Okay? So you look at all the studies that you have and ask yourself, does it matter when this study was conducted? Does it matter whether this study was the first study versus if it was the last study? And what year? So sometimes it might be that, so like if you look at in this meta-analysis that we have on the right, you will see that initially you have such wide confidence interval, right? And then the estimate began to stabilize. And by the time you get to this point, you're essentially getting 0.36 regardless of how many new studies that you add. Okay, so that tells us that the meta-analysis that you have here is being influenced by time, right? And, there's some point when the pooled estimate becomes stabilized. There's something that we call the first study effect. And that is the idea that when you publish a study on a research question, the subsequent studies that follow, they are more likely to have the same direction and a similar magnitude, as the first study that was published. That's the first study effect. And some of the reasons why that happens is because everybody else is designing their study to mirror that first study. Okay, so you have something called the first study effect as a result. A cumulative meta-analysis is important in some scenarios where you think that the time when the study was conducted can impact the results that you're finding. And there are occasions where the cumulative meta-analysis is the entire paper that you're doing. You might just do a paper that shows that the time of a study, maybe there's already meta-analysis that has been done, but you want to do a study that just shows that your results depend on when the study was conducted, and that's an entire analysis. So that's cumulative meta-analysis. If you want to do this by hand, in Revman, you will have to do it yourself. You will sort the studies by year, and you will start adding those studies one by one and capturing the estimates as they differ. So maybe the first study that was conducted in 2000, you add that, and then you add the second study that was conducted in 2001, you compare the results that you have. Then you add the third study that was conducted, you compare, you add the fourth study. These estimates are pooled estimates. They're not individual study estimates. These are pooled estimates. So each one of these is a pooled estimate. So it's almost like this is, if you had a meta-analysis, this is one meta-analysis, this is another meta-analysis, this is another one. This meta-analysis has only one paper, so it's not really a meta-analysis. This meta-analysis has two, which is study 8 and study 12. This meta-analysis has 3, which is 8, 12, and 7. This meta-analysis has, 1, 2, 3, 4, 5, 6, 7, which is all of these studies contribute to this meta-analysis. And then you compare the results and look at how they're changing, and you make up your mind. Do you think that these results are meaningfully impacted by time trends or not? Any questions? Any questions?
Thank you. It's not a question, but just to say that really, we would expect it to change normally, because if we have new studies, I think that's the whole purpose of meta-analysis. Maybe the first studies got something positive. The second study, a year later, then got something negative. It will naturally change. But I think the concept, I understand it. Thank you very much, sir.
Yeah, that's great. But in some situations, right, you can clearly see the year when the results become different. So in that HIV situation that I talked about, for instance, you might find that the moment people started initiating antiretroviral therapy at the time of diagnosis, all of a sudden your study findings are no longer significant. Right? And maybe I can find a cumulative meta-analysis that shows this, and I'll share with the class, where you can clearly see that there is a change in the trend when you add new studies. And that it's not necessarily just because you're adding new studies, but because there is something fundamentally different based on the time. And then you see the pattern. You see that, oh, maybe all of these are on the right, and then all of a sudden the meta-analysis is now on the left. And you can clearly see the pattern. In this case, there is no clear pattern in this one that I've showed you. And maybe I should have added that to this slide so you can see the picture. All right. Any other questions, comments? So I wanted to quickly highlight, that there are differences in the software. I think we talked about this a little bit. Each of the softwares that we have taught have their own, strengths and weaknesses. Revman is point and click. It's very easy to use, as we have shown. SPSS also has a major point and click interface, that's also easy to use. R is entirely code-based. SPSS has its own code too, but most people use it for point and click. So SPSS is sort of like the middle between Revman and R. But being code-based means that R is fully flexible. You can do a lot with R. That's people are continuing to generate new packages, modify the packages in R to help you do additional analysis, right? So each of these are different types of meta-analysis that we've shown in this class, and how do you do it in Revman, okay, and SPSS and R. This is EGAR, that should be G, sorry, 2 G's. So all of these, you can see that there's a lot that's possible with, regardless of the software that you have. Almost everything is possible. It's just small differences here and there. And so a lot of the things that you need to do, you'll be able to do regardless of what software you use, okay? It's on this second page where it becomes a little more tricky. You will obtain the I-squared and the Q statistic regardless of the software. You can do meta-regression. You can actually do meta-regression in SPSS. Apologies, that's wrong. You can do meta-regression in SPSS and in R. You can obtain prediction intervals, but you cannot do that in Revman. You can do subgroup analysis in either one, but that's the only thing that you can do in Revman to understand heterogeneity. Now, I talked about the limitations of subgroup analysis, so you have to understand what you're getting if you choose to do it. And then we talked about influence analysis. So although I said you can't do influence analysis here, if you choose to run the analysis multiple times and do it by hand, then you might be able to do it too. And the same thing for cumulative meta-analysis. Any questions? That is the final slide, I believe.
So,
yeah,
can we include analysis from different applications into one study? Like
you can
get some from R. Okay.
Yeah, you can. Yeah. Sometimes I will generate the funnel plots in one software because I think it looks pretty, and then do the other analysis in different software. So it's possible for you to use multiple softwares. You just have to report that that's what you're doing. Any other questions?
Sorry,
please go ahead.
Okay, thank you very much. This is, I really enjoy all the lectures. This is not for this class, just saying, is this a consideration, sir? I know we've worked on the interventions or effects, to speak, for this lecture, but some of us, and many, are still looking at the small bit of cross-sectional studies where you report prevalence.
Yep.
Is it possible to have maybe just a class? And for example, the example that we chose for our project, at the end of the day, after removing all the studies, we only had 4. And even that 4, they measured different things. But if the prevalence study, for example, I'm almost certain that at least prevalence of smoking, Ibadan, your Lagos, by the time you can pull and say, okay, what is the prevalence of smoking in Nigeria based on the meta-analysis? So is it possible to have maybe a class or something just to go over this? Thank you, sir.
Okay. All right. So the thing with prevalence meta-analysis is that there are actually some things to consider, and I have actually we have prepared the code in R, and the hope was that we're going to teach prevalence meta-analysis, but maybe just do a recording, because I'm not sure that we will have the time to teach a session in it. My greater worry is if you want to do it in Revman, I have to think about it carefully, because I've never done prevalence meta-analysis in Revman before. So I have to think about it a little bit, and then I can get back to the class on, okay, this is what I think we can do. One option is if I can get some time this week, will be to just put together a slide deck and do a recording of, if you wanted to do it in R, Revman, and SPSS, what would you do in one session? But it's fairly straightforward. There are just a few tricks or a few considerations that will help you decide, which path to take. And everything that we have taught, regardless of the software, will help you be ready to do it. It's not very complicated.
Thank you very much, sir.
Yeah, you're welcome. Any other questions? All right. So do you want to
Sorry, sir.
okay, go ahead.
I'm doing a correlational study. Is it pretty much straightforward, or is it a straightforward study if I'm doing it? Because the title is relationship between environmental pollution and hematological malignancy, childhood hematological malignancy. So it's a systematic review and meta-analysis. Is that a pretty much straightforward study, or should I redefine the title?
It's not the title that really matters, okay? The title is important, but what really matters is what you understand by it. So, and the primary papers that you're looking at. So are you looking at, environmental pollution is vast, right? So are you looking at air pollution? So maybe particulate matter, or are you looking at noise pollution? And how are you conceptualizing pollution? So is pollution a dichotomous exposure where you're either polluted or you're not polluted? Or is it a continuous exposure, right? And then the outcome of interest is hematologic malignancies, which is a dichotomous. You either have it or you don't have it, right? So all of those kinds of details, and that's why we ask you to think about the PICO, right, is what will help you to decide what kind of analysis you can do. My impression is that you might be able to do an analysis where for every 1 unit increase in particulate matter, is there an increased risk of hematological malignancies, and you would obtain relative risks. And so if you obtain relative risks, that means that you can do a meta-analysis of ratio measures, which we looked at the first time, right? That was the first Revman session, meta-analysis of ratio measures. So if you go back and look at that, it's essentially the relative risks, and that's what you would use. So the fact that it says relationship doesn't mean that that there is something different from everything that we have learned. That's why you always have to break it back down and ask yourself, what data are we using in this study?
Thank you very much, sir.
You're welcome. Yeah. So one of the things that I'm hoping that we can do is we will likely send out an assignment, right? That might be an option. So it will be optional for you to complete it. But one thing we are likely going to do is that some people are really keen on certificates for the class. And at the beginning, we said that for you to get a certificate, we're going to require you to do a post-course assessment as well as the group project. So as an alternative to the group project, the other thing might then be that maybe you will have to complete that assignment. So we will send out information about this in the next week or so, just to give people more opportunities to be able to learn. That's really the focus of all of this work that we're trying to do. So I hope that this class was useful, and that if you have any questions or challenges along the way, you will reach out.
Thank you very much, sir, for the class.
Thank you. Yeah.
Thank you very much, sir.
You're welcome. Yeah.
Thank you very much.
Some people who haven't spoken at all today, and I hope that they have been able to get along in the class, and that this was useful for you too.
Thank you very much.
Yeah. Thank you, everyone.
You.
You're welcome.
Thank you.
All right. Take care.